Hopefully this is recording. These are the solutions to the Chapter 25 conceptual questions and problems. So our first homework chapter, that is, on electricity. I think we went over most of these in class, the conceptual questions, so I'm going to kind of leave them there. This spot was I think question 12 was one of the ones that was more challenging, so you may want to look over that solution. And then this was just Newton's third law. So for the problems, if you're trying to find electrons transferred, the rod was positively charged, and it was a non-conductor. It was like plastic, and the sphere was a conductor, so made of metal, I assume. And the sphere became, I told you how many coulombs coulombs were transferred. So electrons are the charge carriers, so I converted nanocoulombs to scientific notation. This conversion of how many charges are there in 1 coulomb let me know the total number. So I was asking you to find the net charge on B. So if you take a look at that, make it a little larger. A, B, and C are here in a line, 2 centimeters there, 1 centimeter there. So I can do Coulomb's law twice between A, B, and B, C. I do need to note the direction of the force, so I know whether vectorially I would add or subtract them. In this case, I add them. So the net force on B is down 4.05 times 10 to the negative 4th newtons. For 33, these are at a equilateral triangle. So we're asking for the force on this charge. So you want to think about using symmetry. Obviously, the charge in the lower left and the lower right both act on the top 1 nanocoulomb charge, and they'd have the same magnitude of force, so I only need to do the calculation actually once, and that's 1.8 times 10 to the negative 4th newtons between the 1 nanocoulomb and one of the 2 nanocoulomb charges. But if we look at the symmetry here, we're going to end up having the forces push up to the right and up to the left. Because of the symmetry, the horizontal forces cancel out, the vertical components would actually add up. So if I can find the vertical component for this force and then multiply it by 2, that would give me the net force. So I just drew a little triangle here, used some trig, because that was the hypotenuse, and so opposite over hypotenuse is a sine function, so gave me that amount, and then multiplied by 2. For 37, I think we went over this one in class, and I did a sample somewhat close to this. The magnitude and angle of the force acting on the plus 5 nanocoulomb charge. And we did go over this in class, but if you'd like to look at it again, I think it's useful. So I got this hypotenuse is 5 centimeters. Figured out that between the 5 and the negative 5, the force was to the right because it's an attractive force on this charge, which is what we're interested in. And then we need to find the force between these 2 charges. I got that with Coulomb's law, but I had to break that into components. So whether you think of this as a 37-degree angle or this inside part is a 53-degree angle, doesn't matter as long as you apply the trig correctly. That's why I do another diagram here. It definitely helps me out. And this was a free body diagram for both forces acting on this charge. So I'm thinking that I should have a force down. I'm not sure yet to the right or the left based on the magnitude. But now when I get these forces for actually I don't know why I did these in green because it's for this positive 10 nanocoulomb charge, so sorry about that. I get these are the components caused by the charge in the upper right hand corner. And so I get the amount that's left and down. The horizontal forces, I figure out that I subtract those because they're acting as opposite directions. I end up with a net force to the right, net force down. Drew a triangle as a result to help me make sure I think about it correctly. And this is below x-axis. Technically, I think one of the weights, because they like to correct me, makes them feel good about themselves, but that's okay. I would also, you could say, clockwise from the plus x-axis. So I will adjust that for them. Sure. Okay. The last two problems, this is very similar to the last part of the sticky tape lab we did. So we've got gravitational force and electric force acting repel. The electric force is repulsive. I can figure out the ratio of those forces with the angle. I know the gravitational force because that's easy to calculate. I can figure out the distance between these two also using trig. So this distance to here, or I guess I showed it better over here, is 0.342 meters. So the distance between both these charges is 0.684 meters. And now I can think about the fact that, say, on this charge here, I've got a gravitational force down and electric force to the right, give me a 20-degree angle. So using trig again, I can get the magnitude of the electric force. Go back, since both these have the same magnitude of charge, Q1 times Q2 is Q squared. I get the force. Remember, you would need to take the square root here. I kind of did that without showing you, so I was naughty about that. Electric field was given. The general electric field formula is a ratio of force on the charge divided by the magnitude of the charge, and we're actually trying to find the magnitude of this charge. So we know the gravitational force down. We're given the angle, 20 degrees. So once again, I can find the electric force to the right, and then I simply rearrange that general formula for electric field strength to get the amount of charge. And this charge has to be positive because electric field lines point from positive to negative, meaning this area over here would be positive, and this area over here would be more negative, and therefore the charges would experience a force to the right. So I hope those help. I would look over those. I'd definitely make sure you're starting to get more comfortable with electrical problems and electrostatics. Thank you. Have a good day.